Hello, everyone. This is Pramod Vadravu, your host, and we have Tammy Epperson here. She's the president of Oncology Data Systems, and she's going to talk about how she's going to use how she has been using computational thinking aspects in her problem solving, daily problem solving that is to do with oncology data systems. Hi, Tammy. How are you doing?
Hi, I'm good, Pramod. How are you?
Good, yeah. Yeah, thanks
Great.
for joining us.
You bet.
I'm sure you're all doing your own thing with your busy systems there. And yeah, can you talk about a little bit about what you do at Oncology Data Systems, how you solve the real world problems?
Yeah, absolutely. Okay. Hi, everyone. My name is Tammy Epperson. I'm a software engineer. I work for Oncology Data Systems. So what does my company do? Well, what we do is we write dose calculation software for radiation treatment planning. And to try to explain that, I'm going to show you a quick video. So I'm going to share my screen here. And okay, so when people have cancer, one of the ways we can treat it is by using radiation. And this man you see here in this video is being treated for a brain tumor using a machine called a linear accelerator. So this is one of the most common methods for treating cancer with radiation. It's not the only method, but most of the time this is the one you hear about. On the man, that's called the gantry. And that delivers radiation. You can't see it because radiation is invisible, but it's delivering radiation dose to this man's brain, and it's going to help stop the cancer cells. So I'm gonna stop the share here. Okay, so the great thing about radiation is that it stops the growth of cancer cells, it kills existing cancer cells, and healthy cells. So we have to be really careful with it. And what we try to do with radiation is send a maximal dose of the radiation to the tumor, but we want to be very careful not to send too much radiation to the surrounding, structures, organs. Maybe it's a lung, a brain, whatever. So that's our goal. And because it's so important that we kill the cancer without hurting the healthy tissue, there's a lot of checks and balances that are involved when you treat a patient with radiation. So my software is one of these checks and balances, but there's also measuring devices that measure the projected dose before the patient's treated. There's treatment planning systems that are crazy sophisticated that make sure the patient's getting the right dose. So all of these systems have to be in agreement that says, yeah, the patient's pretty much getting the dose we calculate before he can even be treated at all. We take it really seriously. So how do we use computational thinking? Well, calculating the radiation dose to a patient does sound pretty complicated. And I mean, it is. So one of the ways we make it easier is we break it down into steps that are much simpler. So it's called decomposition, but when calculating a dose, we have to think about certain things. Well, what kind of radiation is it? Because different types of radiation behave in different ways. And what do we need to do? Are we calculating deep within the patient? Are we calculating near a bone? How big is the field? And once we know each piece of data here, we can better understand how to structure our algorithm, which I'll talk about later. Basically, we'll better know how to calculate the dose. So the other thing we have to do is, this is a process called abstraction. So we have to focus on what's important and try to make sure we ignore the stuff that isn't important. There's a lot of data here when you're talking about treating a patient with radiation. So for what I do, I calculate the dose to a patient. What do I need to know? Well, I need to know what type of radiation, what treatment modality. Is he being treated with a linear accelerator? Is he being treated with, like, for example, a live radioactive source that goes inside the patient? Where is this patient being treated? Are we talking about a lung tumor that's going through a lot of air? Are we talking about, maybe a esophageal or brain where there's not maybe so much air. So that's another thing. How big is the area being treated? That's pretty important for a dose calculation. Where's the point? Like, we calculate dose specifically to one point in the patient. So we need to know that. What don't we need to know? Well, I don't care how a linear accelerator works. I mean, I don't need to know that, so we can ignore that. I don't need to know the patient's medical history. I mean, that's pretty important to the patient. It's not important when calculating a dose. So, that's another thing we ignore. I don't need to know anything about the medical team, the hospital this patient's at. So we have to identify just what parameters our software needs to work. So that leads us to another thing. There's all kinds of possible radiation treatments. Like I mentioned, there's one called brachytherapy. It's where you have an isotope, a radioactive isotope that actually goes inside the patient. There's the linear accelerator and the video. A tiny little linear accelerator on a robot arm. So, and there's also one called gamma knife, where the patient's head actually goes into a machine containing live sources. It's pretty interesting. The calculations are slightly different for each type of radiation, but some aspects of it are the same. We still need to know how the radiation behaves. We still need to know, and by behaves, I mean how the radiation interacts with the type of tissue. Like, brain tissue is different from lung, which is mostly air, which is different from bone. So no matter what type of radiation, we need to know that. We still need to know the size of the field. We still need to know the point. So basically, this is us looking at patterns. This is pattern recognition. So that helps us group together some things that are the same, and then, and then once we know all this information, the last thing we do before writing our software is we have to put together an algorithm. We have to go through step by step, like a recipe, like if you were baking cookies. You follow step by step, what do you need to do? So here we think, okay, we know the type of radiation. So this is the calculation type that we need. Okay, we know the calculation type. What are the parameters that go in this calculation? Well, we need to know parameter A, field size, say. Well, how do we get that? Okay, here's how you calculate field size. So I basically break this down into manageable parts, and before you know it, you have a pretty complex dose calculation, but it doesn't feel complex because we were able to use computational thinking to help us get there. So basically, calculating radiation dose is pretty complicated, but so are a lot of things. The trick is you'll be able to solve the most complex problems pretty easily.
Yeah. Thanks a lot, Tammy. That's a wonderful explanation. You actually started out with abstraction, then you have decomposition, then pattern recognition, and finally algorithmic thinking, right? So it's beautifully explained. It's definitely very. I came from, structural engineering background, and this seems pretty complex to me as well. So decomposition is definitely, it'll help you to break those complex problems into smaller chunks, right? To see what is that we can solve. And now once you have that, you can obviously use abstraction to see if you can derive like you were saying, you can weed out all the unnecessary elements and focus on what is needed to solve the problem. Then you can see what all the commonalities, to see if you can identify some patterns. Then finally, you put everything into multiple steps, step-by-step procedure. Then you can write an algorithm to solve it. It's very, very nicely explained. Absolutely. Thanks a lot.
You bet.
Share it.